We have different methods we can indicate the speed of a motor or the speed of a device. We talked about these the other day. We have what we call incremental encoders and absolute encoders. Are you okay with those? Yes, no. Everybody okay? So what we have here is we have a incremental encoder. See if this thing will focus in on. This is the incremental encoder. Can y'all see the little eyes in there? And this is a through the beam, but this unit right here is called an optical interrupter. But it's basically a through the beam sensor. It's just that the two units are built into each other. So one side is the transmitter, one side is the receiver. What we have is we have the optical encoder is spinning through the thing. And then it's powered up. And then when I look at my oscilloscope, I have it all the output of my encoder. As I turn it, y'all can see it's going to be hard, but you can see it actually gives it pulses, right? Now this one, it has 8 slots on it. So that means for every revolution, we get 8 turns, we get 8 pulses. And then I'm going to go ahead and turn this back on. Now this is giving us the time. So as I slow the motor down, time goes up. If I speed the motor up, time goes down. I follow this so far? We're okay. So this is my setup. This is the, if I can get it. Yeah, so, oops. It's right here. So this is wired on the bottom. I can show y'all, but this is power for the encoder, and then this is the output of the encoder right here. So this is where I have my scope. So I've got this speed indicator up there that's indicating the speed, and I don't think it's giving me the right speed. So what we do is, if we have this device called an oscilloscope, which is most electronic places have, and we can actually look at the output of the encoder. And then we can look at what it's given us and determine if what the display is displaying is correct. But only if I understand what's going on. So this is the oscilloscope. What I'm going to do is I'm going to freeze it. So there's 8 pulses on here. This is the speed of my scope right here. So that means I have 500 microseconds for every division. And then I have how many divisions? We start right here where it crosses. I have 1, 2, 3, 4, 5 and a half divisions. So how fast is the motor run? I'm listening.
Back up a little bit. You said each one of those waves, each cycle.
And what we're doing is we're measuring what we call a cycle. A cycle is a repetition. So a cycle, if we start here, then what we're doing is we're going to where it goes that does that again, right? Let me move it over a hair, and then I'll refreeze it. So what I'm doing is I'm making it cross on the center line.
That looks like 15.
Well, this is, every one of these are 500 microseconds. So this would be what? That would be 500 microseconds. That would be 1,000, right? So what we do is we come over and count. 1, 2, 3, 4, 5. So it's 5 now. Okay, microsecond. Okay, all right. Now, that would give me the time per pulse. How many pulses do we get per revolution? 8. Okay. So I'm trying to figure out the speed. So how much we got? About 2,500 microseconds. Okay. Everybody okay? Or 2.5 milliseconds. Okay, so what was the next thing? So we got this number, and of course you can leave it in microseconds if you want to. So 2.5 milliseconds. Per pulse, right? What's the next thing I would do? Good, great. I'd multiply this times 8. You're here, Jerry, why? Why?
Well, you gotta have total.
Yeah, you gotta have, when we do speeds, we do revolutions. We don't do pulses, we do revolutions, right? You understand? So I'm gonna multiply this 8, and this will give me the time for 1 revolution. Yes. No, it's this. It's 2,500 micro, but that's not legal engineer notation, right? Y'all understand? So what we're trying to do is make this as small as we possibly can. So I'd move it 1, 2, 3, and then I'd say 2.5 milli. Okay. Second. So this right here would be 20 milliseconds. Okay. Well, that's how long it takes. Now what we're shooting for is we're shooting for this. And what does it stand for? Revolutions per minute. So if we get 20 milliseconds for 1 revolution, how many seconds would we get for 60 revolutions? Which would be a minute, right?
I mean,
It's just a multiplication, but what we're going to multiply this by? 60. Okay, so we'll multiply it by 60. And what does that give us? Well, no, we're not in RPM yet. We're still in time. Okay. So we got what? Or 1.2 seconds. Oops. 1.2 minutes. So this would be like in AC, we have this guy right here. Okay. And this is the rate. This is the time. But these guys are just constantly doing what? Repeat. Everybody understand that? So what we got, AC, if I measured this right here, this is just what we did. This gives me 16.7 milliseconds. But we don't rate these in time, we rate them in the rate that they occur. The rate they occur is what we call the frequency. We call this right here a watt. Anybody remember? One of these guys, we call it a watt. We call it a cycle. So the rate, which we call the frequency, would be the number of cycles we get in we call it cycles per second. And then Alabama, we use the name hertz, by the way, to represent cycle per second. And we abbreviate H, lowercase z. So if I know this, if I know one cycle takes 16.6 milliseconds, then what would be the rate? Well, what we do is we can take 1 over the time, and this will give us the rate. So I can come over here and I can say hertz would be equal to 1 over 16.7, but it's actually 16.6666. And then this would come up and give me 60 hertz, and this is what our power company gives us over here in the United States. So we got this right here. If we did it right. So what would be the speed? So this is the rate. So it looks like I should come over here and take 1.1 divided by 1.2, and we've done something wrong. So 2.5 milli, right? Times 10 to the negative third. Okay. Times 8. Then we take the reciprocal of that. So somewhere we got off. I'll take the reciprocal of that. Sorry, we did it backwards. I take the reciprocal of that, and then I multiply this times 60. So we multiply by 62 soon. So the motor's running at what? So we multiplied it by 60 before we took the reciprocal, right? You understand that? So watch this. So I'm going to say, what was our time? 2.5 milliseconds.
1 divided by 1.2 is 0.83.
Wait a second. So watch. So I'm going to say we have, what do we have? We start off 2.5 milliseconds, right? So this is times 10 times 10. No, I messed up. So 2.5, messed up again. 2.5 times 10 to the negative third. Okay. Now I'm going to multiply this by what? By 8. That gives us our time per revolution. Okay. Then this is where we're supposed to, then we take the reciprocal of that, right? That gives me revolutions per second. Now I need to convert it into revolutions per minute, so what would I do? So what we did wrong, or what I did wrong, y'all had nothing to do with it. Okay. So what we need to do now is this is the time per revolution, right? You understand that? Now I need to get it into the speed. So what I'm going to do is I'm going to take my speed in revolutions per second would be equal to 1 over 20 milli. What does that give us? I'll leave my calculator up. So I started off taking 2.5 times 10 to the minus third. That equals that. Then I'm going to come up here and I'll multiply that times 8, which equals that. So somehow we did that first one wrong. So somebody said 20. Huh?
Yeah. 2.5 times 8.
So 2.5 times 10 to the minus third, right? And then times 8 equals 20, right? Then what do I need to do now? Then I would take the reciprocal of that, and that gives me the revolutions per second, right? Y'all follow this? And then I do what? And I multiply it by 60, and then this gives me the revolutions per minute. Are we okay? So first thing I started off and did what? I measured the time, and we got what? 2.5 milliseconds. And this is the time per pulse, or the time per blade. Then I did what? I multiplied it by 8, and then we got what? We got 20 milliseconds. Then we took reciprocated, right? So this gave me my speed, but this gives me revolutions per second. So I'm gonna take 1 over 20 milli, and this gave us what? 50 revolutions per second. And then I took, to get revolutions per minute, I took the 50 and multiplied it by what? 60. And then this gave me 3,000 RPM. Now RPM, we don't, for some reason, we don't do RPM in engineering notation. You understand that? And this is just the industry standard. So we wouldn't say 3 kilo RPM. Somebody might say that, but I've never heard it say that.
And we always multiply by 8.
Well, no, we do for this encoder. So the first thing we need to know about the encoder is the number of pulses it gives us per revolution. If we don't know that, then we're totally lost. And that would be part of the documentation on the encoder that you're using, right? Understand? So this we would always multiply it by 8. Why do we always multiply this by 8? Eric? Because it's got, that's the number of blades it's got, or the number of things it's got. Oh, you got a lot of others. The more blades you have, the more precise you can control the speed. Does that make sense? So most of your encoders will probably have about 200, maybe 200 or more. On that robot over there, you can't even see the blades. You can't even see them. They look like a gray line going across there. If your printer's got an encoder on it, you can't see them. I mean, it looks like a gray line going across there because why? Because they're so what? They're so close together, and our eyes just can't see that. So yeah, we got a time 60. Of course, I don't want to screw around with the encoders on the robots, but we got one robot in there that you can actually see. We can take the encoder off and actually look at it. And it's so dang small that you just can't hardly see it. So here, let's do this one. So let's do one more. Got the motor running. So what I'm going to do is I'm going to just slow it down. And we're still giving us the same reference point, so we're still counting from here. We still have it on 500 microseconds per division, but now we stretch it out this far right here. So how many do we have? By the way, each one of these would be a 0.2. You see what I'm talking about? So what we got is we're counting this as 1, and then we have 5 divisions that divide each major division up. So that means each one of these would be worth a 0.2. So it starts getting kind of complicated, you know, if you hadn't dealt with these for a long time. So the easiest thing to do is just to count the number of major and minor divisions and then multiply that times this right here. That makes sense? So what would be our time per pulse? Well, no, we go 1, 2, 3, 4, 5, 6, 7, 8, 9.2 times that. And then that would give me the total time. Right? Understand? Of course, something you could, if you understand this, you could be. So if it's 5 divisions, that means each minor division would be worth 100 microseconds. So you can do it that way too. But while you're learning to use the scope, just to keep from being accurate, you count the number of divisions. Each one of the minor divisions would be worth what? 0.2. So I'd say 1, 2, 3, 4, 5, 6, 7, 8, 9.2. And then I would multiply it times the time per division. So you might need a calculator. Or you could say 1 millisecond, 2 milliseconds, 3 milliseconds, 4 milliseconds, 4.5, 4.56 milliseconds.
Well, I mean, what time?
Huh?
Multiply that times.
The speed. So this is, well, on the scope, this gives us the speed for every one of these
Yeah,
divisions.
is that 500 or?
That's 500.
What's the M for?
What M?
M right there.
That's the,
M 500.
no, that's just measurements. That means nothing.
Oh, okay. Well, I didn't know.
Right, well, that's a good point.
So that's 500.
No, microseconds. That's the micro symbol right there. You don't put what you're measuring on this side, you put it right here. So that's the mu signal, which stands for micro. So 500 microseconds per division.
That's right. The division that we count. You're not counting the space. You're not counting the space.
I'll call it these divisions. This is the division. This is mine. That's the division. No, this is a division. These are minor. That is a division. That right there. The old square. That's the division. These are minor. That would be 1. That would be 2. That would be 3. 4. 5. 6. 7. 8. Right? Understand? Then let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if I want to divide a 1 by into 5 divisions, that means each one of these would be worth 0.2. That would be 9.2 divisions. Understand? You have major and minor. These are top and minor.
So this would apply.
Now, over a while, you can read these. So what we got?
46.
4.6. But see, after a while, you learn how to do this, and you'd say, well, each 2 of them, every one of them's worth 100, right? You understand? And then every one of them's worth 500, so that means 2 of them be worth 1 millisecond. So that'd be 1 millisecond, 2 milliseconds, 3 milliseconds, 4 milliseconds, right? You understand? And this would be 4.5, and each minor division would be 0.1, so that'd be 4.6 milliseconds. So after you deal with a scope for a long time, you can read it without thinking about it. But while you learn, and the best thing to do is just to do what? Count the number of divisions and then multiply it by your speed. And this is the voltage, so I have 2 volts per division, right? You understand? So this would be 2 volts per division, means now each one of these guys is going to be worth 0.4, right? You understand? So it gets kind of a little confusing. So this would be about 2.8 volts. I'm sorry, 4.8 volts. So after a while, you use the scope for a long time, you learn this. But while you learn, what you need to do is you'd come up here and count the divisions. You'd go 1, 2, point, right? That'd be 2, 4. So 2.4, and then you multiply it by 2, and that would give you 2.8 volts. So that's the pulses we're getting off here. Okay, guys, so here we go. What would be the speed? So we got 4.6 milliseconds, right? Now, on this scope, you can have it measured for you. That's what I did this. I need to. Oops. Of course, we don't let y'all do this feature while you're learning how to use a scope, but this scope will actually measure it for you. So according to that, I got 5.4 milliseconds. 4.6. Are we okay? What do we need to do now?
Take that 4.6.
Not yet. Times 8, because that's the encoder, right? You understand that? Times 8. That's the number of blades on the encoder. And take the reciprocal of that and multiply 60. Yeah, you missed a lot of steps. First of all, we got to get the revolutions per second. So the first thing we would do is we got 4.6 milli times 8. What does that give us? 36.8 milli. Right, you understand. Then I would go to revolutions per second. So I'd come over here and take the reciprocal of that, 3.68 milli. And what does that give me? What's that? 27.1. This revolutions per second. And then I'd go to revolutions per minute by taking 21.7, multiplying it times 60. And what have we got? 1,626. Yeah, revolution per minute. Yeah, because Alabama Power, that's their frequency, 60. Well, no, that's not true. It has nothing to do with Alabama Power. What it's got to do with is how many, this is revolutions per second. How many seconds are in a minute? 60. So if I know the time per second, then I can calculate the time per minute just by taking the time per second and multiplying it by what? 60. So it has nothing to do with Alabama Power. Right? You understand? What we're going is we're going from what? Yeah, we're going from seconds to what? Minutes. And that's all it takes to go from seconds to minutes. So this is the way you can calculate your power bill. So you go out there one day and measure your meter. You go out there another day and measure your meter. Right? You understand? And then you would divide, then you would multiply that times what? 24 for the number of days, then the number of days, right? You understand? And that would give you your kilowatt hour. We had a class one time that we took, and that was one of the things we have to do. All right, anything else I want to show you? One more thing. Okay, now y'all go ahead and take a break, and we'll come back in. What's the difference between an actual load and a radial load? We have a term in electronics on different components, and an example would be a capacitor. We can buy capacitors two different ways. We can buy them with the leads coming out the bottom, and we can buy them with the leads coming out the side. And it's very important when you buy a capacitor to know that, because they mount different ways. We refer to this one as a radial lead.
I changed my way, but not thinking right.
And one thing I remember is the axle on the car.
Hey, I'm in class, I have to tell you that.
The axle on the car. So how does the axle on your car come out? It comes like this. So radial lead would come out the side. So if I've got a shaft, then this would be radial. This would be axial. So radial is in line with the axis of the shaft. Right? That's axial. Radial is perpendicular to the shaft. You understand that? How anybody say these? What's these called? These are called fidget spinners. My granddaughter collects them. I don't even know how many she's got now. So this is a radial load. Sorry, let me get it turned right. So that's a radial load. This is an actual load. So if I spin this, my weight is perpendicular to my load is perpendicular to the shaft, right? Understand that? Because the weight of the big, if I do like this, now my weight is in line with the axis of the shaft. So this right here is a what? This is an actual load. This is a radial load. This is an actual load. So you have different bearings that are responsible for different loads, right? You understand? And this is what they were talking about. So right now, my weight is this way. So this would be a what? This would be a radial load. Now the weight is this way. So this would be what we call the actual load. You understand that? So it depends on how the motor's mounted, how the force, what gearboxes and stuff we put that in. Predominantly on a shaft, our bearing, on a motor shaft, our bearings usually have to support a lot of radial load, because if the motor's mounted like this, then that whole rotor is sitting there trying to do the weight of that. And then plus anything you put out there is trying to push down. If we mount it like this, then my bearings, if I mount my motors like this, then we got to make sure we get the right motor bearings, because normally most rotor bearings are in there for a good radial load, right? You understand that? So now I've got radial load bearings in there, and now my shaft is trying to push down. Now if I've got radial load bearings, they're going to wear out real fast, right? You understand? So that would be all I wanted to make sure we understand. And I found my fidget spinner. That's a perfect example. for different loads. So now this is a radial load. That's an actual load, right? Understand that. So action load is in line with the axis of the shaft. Radial loads are perpendicular to the axis of the shaft.
I think they're used like that. The big like spoke.
Well,
They
they're
call them thrust bearings.
got thrust bearings and they're angled. They're got a helical angle to them, or they got a cone shape. And so they support more on the out, and those are thrust bearings. And sometimes, most times, thrust bearings only work in one direction, so they'll use them in pairs. You'll see them pointing in different directions. So one bearing handles the thrust going this way, and the other bearing handles the thrust going that way. So on your front tires, when you're turning, when you turn, that wheel tries to push itself out.
Yeah.
So you got to have a thrust bearing in there. But all your radial load is not coming this way. Most of the time, those thrust bearings will be mounted on the outside.
Yeah, both over here.
We don't have.
We don't have.
All we got is regular ball bearing.
Action.
Yeah, we support no radial, because they're supporting the weight. So anytime you're supporting a weight, you're going to use an action bearing or some type of sleeve bearing, right? What happens if we got something that wants to push it or pull it? Then we would. So if I put a spur gear out, if I put a helical gear out there, well, helical gears are constantly trying to pull themselves out, right? Understand, just by the nature of the beast. So what we need, if I'm using helical bearings, then I need something that's got a lot of I need a bearing that's got some actual. If I'm using spur gears, it don't make any difference. Spur gears, all the weight is on the radius. An actual gear, we would have load on the wall, on the axis of it. Yeah. So it all depends on what loads you're trying. So that's why they're calling bearings, because they got to bear a lot. The main purpose, of course, is to go from something that's in motion and have the ability to attach it to something that's stationary, right? Y'all understand that? And we need something between what's in motion. So if I've got something in motion and it's moving across something, anything that moves across a surface creates something called friction.
You could have those mounted in this point on that.
Yeah, depending on the load, what the load is. If it's an actual load on the shaft or a radial load, or which one is most. Both of them give you a little bit of the other. Y'all understand that? So if I've got a thrust bearing, it can handle a lot of actual load, but it can still handle a radial load. That's not its big thing, right? You understand? It's designed to handle a lot of actual load. Oops, wrong thing, Rick.